topic would be linked lists and binary trees. So we're going to talk about linked lists and also maybe compare them to arrays. We're going to talk about binary trees, but before binary trees, I'm going to give a quick overview of how a graph looks like and how a tree looks like, and then go to binary trees. And just show you some visualization of how to traverse the trees. Okay, let's see. Linked lists. So let's think of a train, right? When you have a train, you have the end. This is where the operator sits in, and basically you connect trains. I don't know. Cars. Yeah, you connect cars, and the way you connect them is you have this link. You link this with, I don't know, chains, right? So linked list is basically you have these are separate, but you can link them using a pointer for next. Okay, so you have a head, you have nodes. Nodes are your cars, and the links are your pointer that points to the next car. So what I'm saying is, let's say this car at the end, it doesn't point to the head, it points to the next one. So it only knows the next one. Okay. Again, give it also an example of, let's say we have a class, and instead of me, I'll try to memorize everyone's address. It's very hard. I can just memorize, let's say, Amanda's address, and then Amanda can tell me the other person's address. So it's easier for everyone to just memorize. Okay, this is wrong. So linked list is like a train. You can add boxcars and train engines in any place you want. The pointer to the next item in the linked list is like a boxcar coupling the links. It connects the boxcars together. Okay. So in this analogy, the train is the linked list, meaning the whole train with all the cars and the head. That is the linked list. And then the boxcar is the item in the linked list. So each boxcar is an item. And the boxcar coupling, which is the link, again, that is what we call the pointer. It points to the next car. Okay. Conductor is the representative of where you are looking at in the train in linked list. Okay. So here's how it looks like. So you have, let's say, an object. We call this, let's say, a node, and this is a node, this is a node, and this is a node. So both, all of them are separated, and the only way you connect them is you create a pointer. So in this object, you have two things. One is you have the data, and the other thing is this one stores the address of the next object. So whenever you access this one, you access the other object, and so on and so forth. And again, the very end of the linked list, or I say when we have one object in the linked list, it should point to nothing. It's not. Okay, so linked list is still a linear data structure where each element is a separate object. Each element we'll call it a node, which we already called it a node of a list. It's comprising of two items, the data and a reference to the next node. So if you remember in arrays we do have, let's say, 0, 1, 2, 3, 4, 5. The problem with that is, let's say 4 is already occupied. You would have, let's say, put data in 0, 1, 3, and then 5. So you're like skipping. It's like going to the movies with your friends. Instead of getting the seats, your friend, you have to ask him, oh, you need to sit somewhere else. So that's one of the problems for array. Unlike for linked list, it doesn't matter where you are. I can just point. Okay. The last node has a reference to null, which we showed here a while ago. The last node points to null. So this would denote, let's say you're traversing your linked list and you find node, you would know that node is the last. Okay.
the entry point into a linked list is called the head of the list. Okay. The time complexity for this one is
often for access and search, inserted read is O of 1. Worst case is the same, space complexity is the same. I'll show a comparison with
arrays later. I don't think. Oh, there. Next.
So for arrays, you have an access of O of 1. With any index, you can access right away. You can say array and then bracket position 5, you access position 5 right away. However, if you want to insert, usually you would use an API, let's say append or push, and what it does is it traverses and goes to the end and adds it. So like, oh, okay, it needs to go through. And for linked list, though, if you need to access something, that's another trouble because you don't know where the other nodes or elements are. So you have to always traverse the link. Let's say I want the middle one, you still have to traverse from the beginning to reach the middle. Insertion, though, is very easy because you always add to the head. Insert to the front, and then change the point. So if you compare, this is a fast read, slow insert for array, and linked list is slow read and fast insert. And before graphs, let's say we have some good examples here. I think I already told you guys about the movie. Oh, okay. So let's say you're building an app to keep track of your finances. So every day, you write everything you spent money on. At the end of the month, you review your expenses and sum up how much you spent. You have a lot of inserts and a few reads. Should you use an array or a linked list? Linked list? Yes. Mm-hmm. Yep. So given the same scenario, it depends on your use case. If let's say your users need to read it more and not really insert a lot, you insert less often than not, so you use arrays. If let's say you keep inserting but you don't really need to read your data most of the time, you try to do it for performance.
Okay, and then again, same goes with for arrays again. Let's say the problem with arrays though, let's say again, let's go to a movie theater and I'm going out with a bunch of my friends where there's 5 of us, but there's only 3 seats left, right? And now you can't sit together. So another way to solve that is you expand your array. Let's say, okay, maybe let's reserve 10 seats, right? And then at least we'll fit in there, right? And next is keyboard cat, memory use. Yep. Okay. Let's check some visualization for linked list. This. And this is better. So this is linked list using a stack implementation. Let's say let's add input strings. Yes, you can. Add another one. So as you can see, whenever I insert
this top, or what we call also known as head, it changes the pointer to the new one.
And
this one points to nothing, which is null.
Put that bigger. So again, it's kind of like a train. And can we pop, up, pop, pop, pop. Again, this one simulates a stack whenever we add values. It creates a new object for that. And then it pushes it into the stack. And you can just pop it. Okay, so the way to implement this one, I think this is just better to show you guys. So
You definitely need a class node. Why? Because you need to always create a node object. So you instantiate a node object. And it's when you create a node object, you also initialize and create pass an element, meaning data. Whenever I type, let's say 122, it will be passed on here, and then now that node would have a
data inside of it. And then the first thing that it would have as well is
this dot next points to nothing. No.
And usually the functions that we need to implement are
The add, insert add, remove from, remove element, and other helper methods. So that you use this method to create these methods.
So I'm just going to show you, I think, the add and insert add. And again, this code is available for you and all the sources. So when you add an element, when you use the add, you basically create a new node. And you create a variable. And the next thing is, if this dot head points to null, change it.
This dot head would point to the new node. Right? We're just changing the pointers.
And then insertion, though, when we want to insert something not at the beginning, it would look like this. Inserting linked list. Let's see. This one. Okay. This is a good image. Oops, sorry. Image, new tab. So because
The way this is structured, you cannot just insert something. So the way you do it is first you, let's say you want to insert between B and C. The way you do it first is you connect E to C as well. And while B and C is connected, because if you immediately say, oh, okay, I'm going to insert E in between, well, if you remove this connection, now you don't know where C is. So that's why, while this is still connected, you connect another one to C, then now you can remove this, and now you connect B to. So it's just again changing pointers.
right, let's see. Oops. Let's go next with a graphs.
So graphs are, it has vertices and it has edges. And these are the line, and vertices are the nodes. Okay.
I guess I could show you social media graph, I think. So like this one could represent a graph.
Let's say this is you. You have a bunch of connections, and usually the way you map connections in LinkedIn, in social media like followers, following, you use a graph model.
Okay, back.
Okay. So again, graph is a group of vertices and edges where an edge connects a pair of vertices. And It's basically a disjointed union of trees. Okay. You know, trees, on the other hand, are a restricted form of graphs. And if we want to differentiate between trees and graphs, in graph, there could be more than one path, unidirectional or bidirectional, between edges or between nodes. Okay, tree is a special form of graph. Again, it's a restricted form of graph. That's why most of the time in algorithmic data structures, trees are taught first before graphs, because graphs doesn't have a structure somehow, so it's harder to grasp. The tree is a special form of graph, a minimally connected graph, and having only one path between any two vertices. Also, graphs doesn't have a concept of root node, while trees has a concept of root node, and every child have only one parent. Okay. Parent-child relationship. Again, graphs doesn't have a parent-child relationship. In trees, there's exactly one root node, and every child have only one parent. The way we traverse graphs is two things. We use depth first search, meaning go deep first, and breadth first search, go wide first, when we try to search for elements or traverse. In the trees, we also use DFS and DFS. In trees, however, we have multiple ways we can use the depth first search. We can use the pre-order, in-order, and post-order. And also for the DFS, we can use the level order. Okay, we'll talk more about that later. So thing is, you can check and Google and just ask, so when to use depth first search or breadth first search. It says here, if you want to find the shortest path between two nodes in an unweighted graph, you would use depth first search. Otherwise, use breadth first search. Okay. You guys have to research more on this. This is, I guess, more deeper. Trees in real life is this one. And as programmers, we try to make things complicated. I mean, the algorithm makers. So in computing, trees are like this. Okay. Again, this is your root, and you would think of your leaves as your child nodes. Okay. Trees have hierarchical data structure. It's not linear. Okay. Hierarchical. So like an organization chart. Okay. Another example which you guys really love so much is Linux. So Linux file system is using a tree structure. As you can see, you have the root node, and all the folders are either the child or parent of something. Pop quiz, what is user/bin? What? Awesome. What do you use MNT for? Mount what? What type of volume? Block, logical, or okay, yeah, sure. Whatever. Okay. So another thing that you can see or have experience growing as a kid is when you play guessing games, right? We can use a binary tree. Again, for binary tree, it's sorted, right? So let's say you want someone to guess the number 5. I want people to guess the number 5. And someone gave me a number, let's say 30. And I would say, oh, go lower. So now they would think lower than 30, right? And then when they say 7, I would say go lower. So if they go to the left, now they're inside. And then when they say, let's say 1, we can just say, oh, go higher. So they may think somewhere here, right? Until you say, oh, 6, and then say, go lower again. Then until you reach this one. So if you're having fun with binary trees, you can definitely use it
to create a simple guessing game. Another thing that you can use binary trees are when you're creating a, let's say your own dictionary. Let's say create words that starts with A. And it's useful for when you're doing words with friends or Scrabble. And now you just connect all the other letters that could form a word. Just store that. So a binary tree structure. So how does it look like? So again, we talked about having trees having root nodes. This is the starting point. And again, in trees, you would have parents. In this case, the 17 is a parent to 9 and 15 as children. And 9 is a parent to 6 and 5. And 15 is a parent to 8 and 10. And now we also define them as left or right, right? So 9 is the left child, 15 is the right child. Okay? 6 is the left child, 5 is the right child. 8 is the left child, 10 is the right child. And if you want to subdivide trees, you just call left subtree, right subtree. Okay? So more on binary tree structure. So another thing that we also look at is, wow, let's see, so leaf nodes, actually height, the height of the tree. So this, if you only have the root node, and you, let's say, have a function, and you want to check the height of the tree, it should return 0. It doesn't have any depth. Okay. When you now have your first children, you can say you have a depth of 1 or a height of 1, and so forth. Okay. We also call the children nodes that are at the bottom of the binary trees, you call them leaf nodes as well. So kind of like trees. The last one out there are trees. The edges you can think of like branches. Okay. And again, as kind of like the same with linked lists, when you have nodes at the end, it points to nothing. Points to null. So again, binary tree node would contain the following parts. It should have a data, pointer to the left child, pointer to the right child. As we go back to linked list, inside a node, you only have a data and a pointer to the next node. This case around, you have a data and points to left and right. A tree whose element have at most 2 children is called a binary tree. Since each element in a binary tree can have only 2 children, we typically name them left and right child. I hope you don't call your kids like that. Binary trees. Okay. Traversal, again, we have pre-order, in-order, post-order. And let's see. So in pre-order traversal, it is also a depth search. We visit the root node first and visit all the nodes in the left subtree, and visit all the nodes in the right subtree. So what happens here, if you create a function that would traverse in a pre-order way, you would read the data like this. It reads the 7 as a root node. It goes to the left subtree. It reads this one and goes left again. And goes back here and goes to the right, read the 3, goes to the left again. Keeps going left. Or also you can do it the other way around if you want to keep reading the right. Okay, so left and then go down, you read this one, the root, which is the root node, go left and go right. This is all done. Now you can go to the other side, read the root node again, then left, then right. Okay. The other way we can do traversal is we first visit all the nodes in the left subtree. Okay, I'll give you maybe 10 seconds to just look at this first. 10 seconds. 3, 4. Okay, proceed. Okay. So in order traversal, first we visit all the nodes in the left subtree, then the root node. Visit all the nodes in the right subtree afterwards. So as you can see, the first data that was read is 0. So because it wants to visit all the left first, it visits here and reads that data. Then now it goes up, reads that data, goes here, reads that data, and then tries to now go to here. Because you want to visit all the right first, then left again, 5, 6. Sorry, it's 0, 1, 3, 2, 5, 4, 6. Oh, 4, 5, 6, sorry. And then after you're done with here, it goes up, it reads the 7, and then goes here. But again, it doesn't want to read the root at first. You go here, 8, and then 9, and then 10. So as you can see, in this part, it tries to read the root first, or the parent, root or parent, before reading the left. In this case around, it wants to read the very left first. It goes to the parent, and then the right. It goes to the left, parent, which we already read. Oh no, it goes to the left, right, but we have left again. Whenever we have left, we should go left before reading the parent. We go right, but we have left, so we go left first, and then go read the parent, and go read the right. It sounds pretty confusing at first, but once you get a hang of it, it should not trouble you so much. Post-order traversal, you visit all the nodes in the left subtree, visit the root node, visit all the nodes in the right subtree. So as you can see in this sequence of data reads is you go first to the 0, and then goes to the other 2, goes to the 4, and then once it's done, you go to the right, and then parent. And because you've already read this right, you go to the parent. And because you read this right already, you go to the parent. And then now, because we go left, right, parent, right? This is still a parent, so we get right. But we still have a left, so we go left. Left, right, parent. And then now we can go to parent. Okay? Okay. So we have depth first search and breadth first search. Let's see. For traversal. I can show you visualization, I think if we have, but we have the code as well. It's very, very long. Depth first search, it uses the stack data structure to traverse. Okay? To keep in track of the order of the nodes in the tree. Okay? And breadth first search, it uses the queue data structure, so to keep the order of the data in the nodes. Binary search tree, time complexity in average is log n, so half. Worst case, you have to go through all the elements. So access, search, insert, delete is O of n, and space complexity is O of n. So there are many types of binary tree, and there's description for every one of them. When we say a full binary tree, every node other than the leaf nodes has 2 child nodes. Okay. So because number 2 is like a leaf node already, it doesn't need to have 2 child nodes to be a full binary tree. Same goes with 3 and 4. But if let's say 1 only has 3, that should not be called a full binary tree. A complete binary tree, all levels are filled except possibly the last one, and all nodes are filled as far left as possible. So it's kind of like the full binary tree, but this time around I can have 1 child, but it should be in the left only. But let's say you declare that you want it to be on the right. A perfect binary tree, the perfect world, is basically all nodes have 2 children and all leaves are at the same level. So meaning you can't have a children for 3, and that's now not a perfect binary tree because they are not in the same level or height with them. Okay. So I guess this is a 2-child policy. I don't know if they use perfect binary tree for that. Full binary tree. Okay, I think we talked about this already. Oops. So visualization, let's go over that. Let's see, let's go post order traversal visualization. This one, let's see. I think I have it here as well. Visualizations. Okay, this is, let's say first. Now let's do binary tree first. Okay, let's do binary tree first. Okay, let's say we insert an item. Let's do numbers instead. 6. And let's say 2. Let's say 7. And what if we put a 15? Where do you think it would go, left or right? Okay, awesome. And if you put 20, where do you think it would go? I believe it should be right, left. Oh no. Let's see, 1. Let's see, 55. Let's see, 22. Let's see, 14. So as you can see, the binary tree is trying its best to create some order, right? It tries to always keep the higher number on the right and the lower number on the left. Let's see if we can put number 5. Oh, 5 goes here. Same number. That would work. 4 again. If we want to delete something, okay. Let's see. This one. I think this is way better because it was so hard to find a good content. So I can just show you quickly how it goes. Okay. So what happens here is with the breadth first search, you need to have a queue stack, right? It is in order to keep track, and if you need to go back and read the other child nodes. So let's see. So the first one, definitely you're going to start with the root node, okay? And you can output that right away. Sorry, on the bottom, output that right away because you don't need to keep track of it. That's why you don't need to keep it in the queue, okay? Next is when we traverse breadth, we want to go wide. So which are the two nodes that are wide? Left and right, right? So we want to keep track of those. That's why we want to put them in the queue first. And because it's a queue, it's a first in, first out. So what happens now if B, see, B is here, printed, and F is printed. You want to go wide first. And now it's printed, you can remove B. Okay, we no longer need to keep track of it. We can also remove S because we already printed it out. Next is we still want to go wide. We go for C and then G. As you can see on the bottom, sorry, C and G. Okay, now it still needs to keep track of C, I think. Ooh, oops. Okay, pointer's not working, so let's do this. And then now it doesn't need to keep track of C. And now it looks for, because right now,
in G, we still don't have a process G, right? And we have E.
and goes to E, because D and E are now at the same level, and F. So D, E, F are on the same level, and then they're, again, this is a graph, so you wouldn't really call them a parent, but it originates from C. And then now, as you can see, we already printed out G, D, E, F. We can start removing G, but now because when we remove G, we got access to G, now we can add. There you go. And then now we can just remove everything from the queue. So this is the concept of using a queue data structure to traverse using the breadth first. Again, use the queue to keep track of the nodes that you have visited or not yet visited. Okay. On the other hand, though, if you want to go depth first search, let's see, you use a stacked data structure. So we'll start off with A, and then we go down deeper, right? So we go for B, and because there's no more deeper than B, we can just pop B out and put S now. So sorry for this one. At the bottom, A, E, and S has been printed. And then now we're at S, we can go deeper. So it goes, let's say C, and then it still can go deeper, so it goes to D. And now D at that side is at the end, so we can start popping. And C, however, still can go deep. So it goes to E. And then E connects to H, because this is a graph. So it goes to H. And then also G. Okay? And then now G connects to F. And then now we can start popping everything. Okay? Again, this is a graph. And usually the use case for depth first search and breadth first search is for graphs. And again, you use pre-order, in order, traversal. Let's see. Binary search tree. Oh, we're done with that one. In order, pre-order, post order, traversal, visualization. Do we have this? So let's say we have this binary search tree. Let's say we want to search for, I don't know how, in order traverse. Okay, I guess that was way fast. Don't think there's a, is there a good visualization for this one? I guess not. Okay. One thing for you guys to take note about with pre-order, in order, post order is when do you read something, right? I think for that one, let's go back here. I think this one shows you here. You just need to remember this concept for in order, pre-order, post-order. In order, you do the left first, you do the parent or root of that node, and then you do the right. Pre-order is you read the parent or root first, and then left and the right. Post-order is left first, right, then root or the parent. So this is just the concept of what they differ at, but all the three of them are depth first search. Okay, let's go with the muddiest point. Could we as a class have live code a depth first search on a binary tree? Ooh, I don't think that's I just have the code here, but it would take some time to really code this up. So I don't really recommend. But we can do it after the class if you guys want. Okay, so basically creating, let's say, a graph. You create a graph and you put vertices, and then you have to add the edges to connect them together. So you should have a function that adds the edge, meaning disconnect one vertex to another vertex. Sorry. Yep. And because we had a lot of hard muddiest point questions, which I really, really appreciate. So I talked to the two Kevins, the Kevin A and the Kevin B, and then they have mostly similar responses. So I need to review linked lists and binary search tree. I got one question. And then, so Kevin A says all data structure and algorithm works same regardless of programming language. So that answers the question. Still trying to figure out catch and try code blocks. Either one of them is strictly used for debugging. And Kevin A said, and as we all know already during the lectures, is they're used not for debugging, they're used for exception handling. And let's say, for example, the user gets a network connection error. We can write some code in the catch block to handle that in such a way as a retry. You can just say, oh, just connect after, try to connect again after 15 seconds. Not like every 1 second, because it will overload that server. Okay, so heaps are the same data structures as trees. However, with sorted values in them, the book says that a heap is a tree-like data structure in which the parent is bigger than its children. Is it tree-like or is it a tree? So what Kevin A said is heap is a tree, and show them a visual picture for this to help them understand. Okay, thank you, Kevin in the spirit. Heaps. There you go. Looks like a tree. Okay. Moving on. Kevin B, to my knowledge, heaps are conceptually a type of binary trees. Therefore, they can, of course, be implemented as binary trees, but usually are just implemented as array. The one mentioned in the code is max heap. This one, binary heap array index structure. Kevin A said the index rule is assume I, variable I, is the current node's index. The index in the left node will be 2 times I plus 1. And the index of the right node would be 2I plus 2. Okay. Can a tree be considered binary if it's a network? Wow, this is way over my knowledge. So Kevin A said is tree and binaries are two different things. And the network is not always a tree, but it could be, right? Kevin B, no, a binary tree is a tree. A network is not always a tree, but you can build your network just like a binary tree if you want to. Okay. Kevin B is like our hardcore algorithms. It's like preparing for a master's thesis. I think he wants to create an algorithm for a multi-million-dollar patent or whatever. I don't know, but he's always learning about different algorithms that has names, inventors of those algorithms that I really don't know. Even Kevin A is not familiar with. Okay, how is it important to know all these trees exist? Well, thank you, Kevin A. Just saying very important.
Kevin B says it's used everywhere. It's used in searching, AI, and many other things. Binary search trees are trees. Decision trees are trees, yes. And whenever you talk to Alexa, let's say you created a, again, guessing game. You can create a skill for Alexa for a guessing game, and you can map your the user's responses and output with a decision. Tries are trees, which tries mentioned by Ruth yesterday. They can help speed up algorithms you're using. Okay.
Why do we need linked lists? For Kevin A, he said we need linked lists to speed up insertion and deletion operation, which we already showed in the lecture that linked list has that value. Faster insertion, faster deletion, because you can just know where to delete, right? An array needs to copy all of the data to a new place since it needs to be placed in a continuously, I think that's a grammar error, in the memory, but linked list can just simply change the pointer to point to an element. Okay, so if you want to add something new, create it, point to that, done. Okay, for arrays, create something new, you have to access the array, check the array, where can I put this? To make your life easier, said by Kevin B, is when you want to go from an element to another element in the data set. That's for linked lists. And wow, this is very hard questions. Are there any better graph searches than breadth search, Dijkstra, and even our Kevin A gave up? Ask Kevin B. Okay, and he said it depends on the situations. Even these algorithms have many different variations and implementations that have different high complexities and use cases. A simple example will be Dijkstra's can be sped up with mean heap, comparing it to a naive one. Don't even understand what you're doing. But both are called Dijkstra's. Another example is when we have negative edges, Dijkstra's won't do the work. When we just say negative edges, I think when we have negative numbers, that Dijkstra negative cost. Negative cost, right? Yeah. That won't work. Okay. Next is in this case, Bellman-Ford algorithm can do the job. This stands the same if you refer to A asterisk. BFS and DFS are even more general terms. So now you know, guys, if you have more questions in algorithms, please contact this awesome guy. He kind of knows a lot. In reading the text regarding the various trees, I found examples in the code and text helpful in understanding the concept. Okay, examples, some kind of blah, blah. Okay, I think these are just answers to the examples. And I guess that's it. And as always, I put some of my researches for the answers. I'll upload it to the Apprenti TA Center. And then feel free to go over them. And what else do we need for today?